So in this class, we are going to consider our DC machines, but considering actually the speed control of DC motors, as we are to specify speed control is to be determined when you are dealing with a DC motor. If you remember from your N5, actually from N3, when you're dealing with the electrotechnology, we talked about this from our motor. From its conversion of energy, because these DC motors, these DC machines in general, they are there just for the conversion purpose of energy, and specifically for working on a motor. We do understand that in terms of energy, it is going to be converting electrical to the mechanical. So the type of energy, in terms of the power, just going to consider this. Remember, these are DC machines. So the power that you're talking about there is the DC electrical. DC electrical energy, which in actual sense will be talking of the input power. This is being converted into what? Into the mechanical energy. We need just a basic understanding of this, which is being converted into the mechanical energy. So definitely we'll be talking of what? Output power. So on a motor, because we are going to need these your basics of your, just go and revise, guys. The videos are there. Here I'm just gonna peruse through what is needed. As you do understand your motor, whether it's a series connection that we have. We've got series connected to the armature there. That will be in series, or maybe it's a shunt connection. We do understand that the motor, it draws in, it takes in the current, meaning to say we're going to be talking of the load current and having supply voltage, which is at the terminals in that case. So this is our series field. As we do understand, we're having this as the series field, which we can just write as RF. So RF in our N6 is going to be represented whether it is a condition of a shunt. Remember, when we're dealing with a shunt, we're writing this as R shunt. So we're just going to neglect that for now and just consider every field as RF. So I'm just going to use RF to represent the field. Whenever you've got field, I'm going to be using RF. So this is the series field. Knowing that we've got our armature resistance, and talking of the mechanical power, which is our output as we considered, and the input power being electrical, the current flowing, that is the series as we had before. But this is what we're just considering as F. So you're just going to use also F for the field, right? So if F denoting the field, just like we had before, into the armature, which is where we have the armature current, this and that. So you had this, we are basically working on a motor. So I just want you to have the basics of your motor, understanding the calculations of power, this and that. All those, you had it. Also, when you were working with the motor, remember you dealt with the calculation of the back EMF, which was being calculated from the EMF equation, if you still remember your EMF equation. I'm not going to talk much, guys. Remember, it's going to be condition. We have got series, those shunt connections. We're going to talk about that as we are doing examples. Remember, we had the EMF equations. Actually, you dealt with equations. Remember, we've got the first one considering as the general EMF, which can be considered whether you're dealing with a motor, whether you're dealing with a generator, which is E is equal to, that is going to be 2 times the useful flux, the speed that you're given, the pair poles, number of armature conductors over 60C, which is to represent the winding there. Is it lap? Is it going to be a wave? Remember, guys, I just want you to revise back your N4, all this, and understanding of the use of these formulas. And we had the one which we refer as you are to consider a motor, which is E is equal to what? V minus, remember this is the back EMF as you consider what? A motor, you consider this as your back EMF. So it's going to be having a minus there, and you had armature current times the resistance of the armature circuit. All right, take note about this. The resistance of the armature circuit, which is to be considered according to the circuit that you're given. So you need as your basics to understand the types of circuits that you're given, because you need to know the resistance of the armature circuit. Like in a series consideration like this one, where the armature current is flowing, that is where we have this resistance of the armature circuit. So you consider that of the armature and that of the field together. Meaning to say, if it was like this, the resistance of the armature circuit was going to be what? Ra plus Rf. They're in series. So you have to consider this, guys. Revise your N5, this and that, it's going to help you in terms of the connections, whether it is a shunt connection. We are used to this, guys. If it is a shunt connection, remember your shunt, right? So this is the series. Okay, then we've got the shunt. Just going to consider the basics that you will just need in your revisions. So guys, you're supposed to draw like actual diagram, but here I'm just gonna specify what is important. Remember, this is our terminal voltage. Consider the load current. Here we're gonna have the current in the field, resistance of the field, this and that, and the current flowing in the armature where we've got our armature resistance. But in this case, I'm considering the issue of the resistance of the armature circuit. So the resistance of the armature circuit, when it is a shunt like this, where the armature current is flowing, there's only what? The armature resistance. So in that case, it is just going to be equal to the what? To the resistance of the armature that you're given. That is the resistance of what? The armature circuit, where armature current is flowing, where the armature current is having an effect. Here it was having an effect on these two. So you add them. It can be a condition where maybe there is an additional, in that series that you had this one, in this same series, we can have a series with an additional. So guys, just revise your basics because you need those in your revisions. It can be a series connection that we are given with what? With additional resistor. A series with additional resistor. With additional resistor. It can be like that. Remember your connections in series, that is the series field, but it is going to be having an additional resistor. So you put the additional resistor, then you're going to have your series to the armature. So I'm just going to have the basics, not like everything, guys. All right, so this is your voltage, and considering the load current which is being taken in, so this is going to be our additional resistor. So this is representing your additional resistor field. Remember, it's connected in series. And in that case, you're gonna, all those generated DMF, guys, they'll be there. I'm not focusing on, I just want you to understand the issue of what? The resistance of the armature circuit. Okay? That is why there I'm just rushing there. You're supposed to have those generated EMF, this and that. All right, do not consider that. It is important, but for now, I just want you to understand what is important. Having the resistance of the armature. So you're going to see that the additional resistor field and that of the armature together, they are comprising the resistance of the armature circuit, because this is a series where the current is the same. So where the armature current is flowing, it is flowing here. It is the same current that is flowing. It is the same current here that is flowing. So where the armature current is flowing, that's where we are talking about what? The resistance of the armature circuit. So we have to consider in that case, all these resistors, they are in series. We have to add Ra plus the resistance of the field plus the additional resistor, which is being connected in a series. So this is going to give us what? The resistance of the armature circuit. So all these combinations, guys, you have to consider them. In your syllabus, you have to know each and every part. Whether there is a diverter resistor, they can give you a condition where there is a diverter resistor. What is a diverter resistor? A diverter resistor is the one that is connected to the the additional resistor is connected to the field, but in parallel, when it is connected in parallel. So the diverter resistor, gonna call it RD. All right, for the diverter resistor, additional resistor, as we had it on that part, we called RAD like this, additional resistor. So the diverter resistor, this one, it is an additional resistor which is simply connected in parallel. This one, it is simply an additional resistor. It is simply an additional resistor connected, which is being connected in what? In parallel. In parallel to the field. So it is connected in parallel to the field coils, which is to the field winding that you're given. It is connected in parallel. So in a series consideration like what we had, this additional resistor is not here. It is parallel to the field. That is what you're simply having. So it's going to be like this. You have your field winding as usual. All right. So this is your field as usual, the part of the armature, this and that. All right. So this part is just going to remain as it is. But the field is where we are going to have a connection in parallel with additional resistor like this. This is our diverter resistor. That's how it operates. It is connected in parallel. So if it is connected in parallel, we're going to use RD. This is the special name for that. It's an additional resistor, but connected in parallel. So the special name is called the diverter resistor. So we're going to call it RD, and having our terminal voltage, everything is going to remain as it is, taking in the load current. And this current is the same that is here. Take note, it is the same current. From a Kirchhoff's law, what is that you understand? Another current is going to branch here. Another current is going to branch. So the current that is here is of what? The field. So since this is the field, so the current is of the field. This is the diverter resistor. So the current flowing in this branch is going to be called ID, the one for the diverter resistor. All these currents, according to Kirchhoff's law, what is going to happen? They flow. This one is going to flow. This one is going to flow. They meet at this junction. All together, they meet at this point where we are going to have what? The armature current. So in our understanding, we are simply seeing that the load current that we had is the same as the armature current. The load current and the armature current are simply the same. So where this current is flowing, it means also the armature current here is flowing. We are also having what? Armature current. So remember the issue there. It goes to the armature, where we have our armature resistance, all these power output, and so forth. I'm not going to consider that. I want to focus on this part of the resistance of the armature circuit. Where the armature current is flowing, it is affecting these, because it is the one, guys, we are saying, these two, they're the same. Take note here. These two, they are the same. So meaning to say, where the load current is flowing, the armature current is also flowing. It is the same current. So meaning to say, it is the same load current here, which branched here, which affected these two. As which one? These two that are in parallel. So they are going to be part of that resistance of the armature circuit, because this is where armature current is affecting. It is flowing there. So meaning to say, the resistance of the armature circuit is going to be a combination of this resistance of the armature plus these two resistors, which are being connected in what? In parallel. Remember your parallel combination from your basics of your electricity. How do you consider in parallel? The product over the sum in parallel. Product over sum concept. So meaning to say, we are going to have the product of these two, RD and RF. So it's going to be RD times RF over the sum of these two, RD plus RF. Product over sum. So this is the resistance affected together with that of the armature. Combined, they are giving us what? The resistance of the armature circuit. So take note, when a diverter, a resistor is connected, this is what you are going to need. And also, in addition, we are going to see this because it's going to be part of the, guys, we are talking about the speed control, but you're wondering, why am I talking about this? All these, they are going to affect you because they will give you a circuit like this. They will give you a circuit like this, and you need to draw it. You need to calculate this. So you say, oh, this is important. Unless you understand this, then you can fast forward to a part which is important to you. As I said, the additional part that you also need from this diverter combination, let us just have some additional notes here, which is not about, this is not about, remember all these, I was focusing on the resistance of what? The armature circuit. All these diagrams that I'm presenting right now, from this of an additional resistor in series, from this of a shunt, from this of a series, all this I wanted you to understand the resistance of the armature circuit. So this is an additional part which is not to say it is of resistance of the armature circuit, but you need also these calculations. Remember, in your electrical calculations, once there is a parallel connection like this, in terms of the currents, you are simply talking of what? The current divider circuit. Using your current divider rule, you can obtain the current that is flowing across the diverter resistor. I want you to watch, I think it's Industrial Electronics N4. I made a video there on this current divider rule, voltage divider rule. Just make sure you watch those basics, you understand that. So from your current divider rule, if you want to calculate the current that is across the diverter resistor, you use the resistor which is opposite on top. So you're going to have RF over what? The sum of the resistors which are being shared by these two currents, which is, by this current of, which is the supply from the load current that we have. The sum of those that are shared, these two resistors, they are sharing that. So it's RD plus RF, the sum, times what? The current which is being shared, which is the load current. Remember, we said armature current in this circuit and the load current are the same. So in other calculation, this can be presented with armature current. We are going to notice those calculations as we move on with our revisions. Likewise, calculations can be also made to calculate IF using the same concept. So if it is current across the field, you use what? Opposite resistor on top, RD. So it's going to be RD over the sum, that is RD plus RF, times what? What is being shared? What are they sharing? The load current, which is same as armature current. So this is going to help us in our calculations also as we consider the part of our speed control. So I have neglected the major part of our topic and explained something which seems to be useless, but very, very important as we are to consider our speed calculations. When you are to consider this part of your speed control of the DC motors. Let's go back here. Because we needed the resistance of the armature circuit in our calculations, that is why we had to talk about this. So if you go further with this, you master up your N4 revisions. It is important that you do like that. I want us to continue with the part of a speed control. Let's get to the major part of our topic because we're not going to end. There's so many things that we need from our N4, N5. So I want you to do a favor, revise those basics and some basic of your N6 with your textbook that you're using, depending the textbook that you're using, so that we can be together. As we are to consider of the speed control calculations, one, there are conditions to be considered there. There are conditions, as we had in our N5, the conditions in speed control. conditions in speed control calculations. We are going to make the calculations in terms of the speed control. The conditions that are there, we had them in our N5, as I said. Remember, you had those conditions where you're going to work with one, the original condition, where you be given the original condition, or in original condition, you'll be given those values, like type of circuit, is it a series, shunt, whatever that you're given there. This is when the motor is coupled to a load and is supplied at normal voltage. It is supplied at a normal voltage. Supplied at what? Normal voltage. And at these conditions, which is actually the original condition, the motor runs at normal speed. Okay, the motor, remember we're talking of the motor, guys, is at what? Normal speed that you are given, the first speed that you'll be given, and also produces 100% torque. It also produces 100% torque. This is on an original condition. But with the second condition, which is now the final, because you started with something that is originally given, then you consider the final conditions now when the resistor is connected to the motor. In this case now of the final condition, they will give you this. It must be very, very important for you to note. You'll be given this. One, it is going to be the resistor. This will be what we, okay, let me go back here so that you understand me. When we talk about these two, the series and the shunt, these are your normal circuits, guys. These are your normal considerations that you are used to. A series and a shunt like that. So adding something like these circuits that we are now having, where an additional resistor is there, which is in series to the field winding, where the diverter resistor is also connected, which is parallel to the field. These are the conditions that we talk about when they are at the final stage. Something has been done to the what? To the circuit. So you must understand what is it that has been done on these two that you originally know. These are the ones that you basically know from your electrotechnology N3. Series and shunt. Your basics that you are used to. Anything that will affect this basic that you are used to, which is your original condition, is the one that you now consider as your final condition. So this is the one that we are saying. This is when the resistor is connected. So in this case, we are going to find out that the resistor is connected to what? It can be, we saw that from those diagrams. Is it the field? It can be connected to the armature. It depends with what you're given. The resistor is connected to either the field or the armature. Or the armature circuit. So this is the consideration that you need to actually know, because you'll be given there. Like this one, it's a given, that is a given condition. This one. It's a given condition. So you work with that. You're going to consider that condition that you're given there to say, okay, what are they saying? You have to draw a diagram for that condition. First, you had a diagram of the original, then a diagram of this. So the connection of this resistor whether it is connected to the field windings or it is being connected to the armature circuit, what is the effect to the circuit once it's there? What does it do? What is the effect? So with this, we are going to notice some changes are going to occur because of that. This is going to make changes. Current changing, the load current that we had is going to change from the load current that it was to another load current. So you have to consider to say, like we said in our N5, the original condition, you denote this one with 1. The final condition, you denote with 2. So you're going to have 1. This will be 2 for the final. So the load current is going to change. The speed itself is going to change from N1 to N2. The torque is going to change from T1 to T2, considering the EMF that is being induced, or which is our back EMF. It is going to also change from E1 to E2. There are changes which we are going to notice. So when you consider the speed control, these changes are going to affect where and how. Where and how. This is where we have to consider now the formulas, as we had these formulas in our N5. Speed control formulas. We saw that previously in our N5. From the main speed control formula, it states that E1 over E2. Because of time, guys, we're just going to write our formulas where these formulas were being taken from. Just also consider textbook because they explain differently. So just also consider that for the basics. Remember, this is what we had. Assuming that the flux is proportional, which is our useful flux. We're assuming that the useful flux is proportional to what? To the field current. So in actual sense, this formula was supposed to be written with the useful flux. It was supposed to be N1, useful flux, N2, the useful flux like this. So you must consider with the question, guys, that you are given, because sometimes they will give you the field currents, you work with that. Sometimes they will give you the flux, you work with that, because flux and field current is simply proportional. So where there is field current, you just put what? You just put a flux there. This is what you had from your speed control formulas. As you are to consider this, it is not enough only for us to say, okay, this is speed control. We'll be given some consideration because we are talking about torque also here. It's going to change T1 to T2. So they are going to also use formulas that are to consider torque also. So we have to consider the torque formulas also that you're going to need as you are to consider the part of what? The torque. Because it is there as we saw T1 to T2. So the formulas, T1. So in that case, we have a lot of formulas that can actually be used. I'm going to also show you another part. So we've got T1 over T2 is equal to, so the first part, all right, very sorry for that. So let's just hope this is not going to affect us, guys. Not these networks and these boards. So you've got the condition. Remember, I've got final and initial. Why is it increasing? While least I'm not increasing it. All right, very sorry, guys. Like I said, when these boards, when you write a lot of things, they just tend to be something else. But we just hope you're going to be able to finish up our class so that we do have revisions. So this is going to be given. Remember, this is I1, IF1. Then we're going to have armature current 1 over IF2, armature current 2. Remember, you consider 1 and 2 for 2 speeds that you're given for 2 seconds that you're considering original and what? The final. We are going to consider that when the torque is proportional to the speed, we can also equate this to be equal to the useful flux 1, armature current 1 over the useful flux 2, the armature current 2. Sometimes if you simplify, this can be reduced to N1 over N2. So in your calculations, we are going to be focusing on this part. This part of N1 and N2, guys, is something that you have to consider back to your N5 there. So now you have to consider this part that you're given here. So these are formulas that we need to consider when the torque is proportional to what? The speed. This is an assumption that is being made. These formulas, assumption. We're assuming that torque is proportional to speed. We can also assume that, assuming that the torque is proportional to the speed squared, they will give you that condition. When they give you something like that, this is all what you're going to have. You're going to use your formula, T1 over T2 is equal to, so you're going to have flux 1, armature current 1, this will be 2, armature current 2. Then in terms of the speed, we are going to have this as N1 squared over N2 squared. When assuming that the flux is proportional to N squared, this is how our formula is going to look like. So also in terms of the torque, there so many things can be stated because it has to change. So you have to consider difference, assume that the torque has been reduced maybe by 10%, maybe it has been increased by 10%, maybe it is equal to 70% of what you're given originally whenever they talk about the full load. When we are talking about the full load, remember this is where at the original conditions. Original conditions are the ones that you're considering at what? At full load. So when they give you a torque to say this T2 is this of at full load, they're just talking about this T1 at full load because these are the conditions for what? For the original. These values here are at what? At full load. So whenever they say this torque is a certain percentage, it is reduced to 20% of full load value. Full load value. The value at what? Original condition. That is what they are trying to say. So those are the conditions that you will need depending with the situation. Remember from your mathematics, a decrease you subtract, an increase you add. So all those we'll see as we are to make our revisions. I talked about that actually in our N5. So considering your N5, make sure that you go through that. So we're going to consider a typical example that we're having here. As we consider this example, we are also going to need, so I don't know what is the effect of this PDF, because if I zoom like this, you see just 40%, guys, is out of control. I don't know if you're gonna be able to understand me if I do this so that we can be able to see our question properly. So you're going to notice that there are some steps that you will need when answering questions as you had in your N5. Remember, this is the question. So make sure you're supposed to read that question carefully. Whatever that you are given there, supposed to interpret it and draw the diagrams. And draw diagrams. So you're going to draw the diagrams showing the two conditions. Meaning to say, we're going to draw our diagrams showing what? Our original and our final. This is what you need. And from there, you can use the main speed formula, use the main speed formula, main speed formula, which we have there depending with what you are given, your main speed formula. Remember we said flux is proportional to the field current. So on that formula, you will notice what is needed, what is supposed to be calculated. So tick everything that you're given, circle what you need to calculate, all those, we're going to talk about that from that main formula. So after noticing what need to be calculated, guys, you definitely have to calculate what? The needed values. Calculate the needed values from this. Remember your speed. Yeah, there's a condition that you're given then that you need to answer. You have to go back to that formula after calculating. So meaning to say, definitely you're supposed to substitute values that you obtained when you're calculating here. Substitute the values into the formula. Into the formula. By substituting into the formula, what is it that you need? That is to solve for the unknown, for what is needed. Solve for the unknown. What is it that you are being asked? What is it that you're being asked? So we can have the whole day, guys, talking about this speed control, this and that. So like I said, please do revise your N5. That can help you a lot. So we have a typical example that we are going to consider, like we have here. They are saying a shunt wound. This is our question. A shunt wound. It's a shunt wound DC motor. Draws this, whatever that you're given. Then if you read your statement, you're going to get to this part where they are saying the full load. So it's here, sorry for this. This is supposed to be the full load speed of the motor is, we are given that. Then from there, they're now saying the torque developed here, the torque developed by the motor is reduced. Take note, is reduced by 20%. So there's an effect there on what? On torque. That's a condition that you're given. When? What caused that? What caused that? They're saying when a resistor of 1 ohm, this one, is connected in series to the what? To the armature. It is connected in series to the, this is the effect now. That is where you get your original and your final from those two, from that statement. So the original is what? Basically a shunt as it is. So you have to draw that. All right. So let's just have our stages. All right. So as I was saying, guys, you see, everything is actually going to restart, but let us just answer our question. This is the effect that I was saying, that we have a lot of things like this is gonna actually affect. But let's just see, because we need to finish up this. So I'm just gonna retake everything because here everything is just being affected, guys. Let's just hope it will be able to finish up. So they're saying it's a shunt DC, as I was saying. So this is your original condition. So you are simply going to need original condition. Let's just see. All right. So that's our original condition here. So I'm going to call it 1. And the final, I'm going to call it 2. Final condition. So this one, we're going to call it 2. So as for you, you can just like check the formulas that I've written. You can just reverse your video so that you can see the formulas. As for me, now it's impossible, guys, for me to show you the previous page because everything just got resetted. So this is it, guys. Let's see. The original condition we are given that it's a shunt wound DC motor. So you have to consider a shunt wound. Remember, a shunt wound, as you are used to, you're going to have your sketch. Okay, this is the shunt parallel connection as we are used to, and we're going to have the part of our armature. All right, so this is it, guys. Remember, this is a motor. This is your mechanical power output, and this is what you have there. So it draws 45 amps, meaning to say from the load. Remember, the current is being taken in. It's a motor. It takes in the current. So the load current is given there, which is 45 amps. From what? A 200 volt DC, meaning to say the voltage that we are having there is 200 supply. The resistances of the armature and the shunt, they are being given respectively as we are given there. So that of the armature and of the shunt. So the one of the armature is the first one that we are given since it is respectively 0.15 ohms. That of the field, which is the shunt winding. So the resistance of the field, you're also given here. Have your sketch. The full load speed, like I was saying, that is originally. So N1, that is 1000 revs per minute at full load. Remember what I was explaining from those formulas, that is at full load. Then they're saying that the torque that we have on this part here, the torque developed by the motor is reduced by what? 20%. Is reduced by 20% when this is the condition that I was explaining. So let's talk about being reduced. To be reduced, that means originally it was at what? Remember I said it is at 100% when it is at full load. So T2 has been reduced by 20%. They're saying reduced from 100%, we reduce, that is to subtract simply 100 minus what? Minus 20. That is of what? Of the original one at full load. So guys, 100 minus 20 is simply 80%. And as a decimal, if you divide by 100, it's going to be 0.8 of what? Of T1. So this is just a condition to be taken and to be used about the torque. This is what we have when we are to consider our torque. When this torque is being reduced, this is when the condition that made that, what was it? When a resistor of 1 ohm is connected in series to the what? To the armature. This is your final. This is what caused all this. The resistor was connected in series to the armature. As we have this is the original. But the part of the armature here, part of the armature. Okay, we're going to talk about this is 1, this is 2. But let's just see. Part of what? The armature. There's a resistor there. That is now as an additional resistor. So meaning to say you're going to have, as it was on the original diagram, a shunt connection that you had, as you had before. A shunt connection as you had, meaning to say we have that. But to the armature, there's an additional resistor there. So you're going to have an additional resistor. So the part of the armature is just going to remain as it is. This part is just going to remain as it is. You had your P out, isn't it? Only that there is now an additional resistor which is connected in series. And we are given that this additional resistor of what? Of 1 ohm. So this is equal to 1 ohm. So this is what you're going to have, guys. Then they are saying, calculate the new speed, assuming that the field coils are unsaturated. We need to calculate the speed of what? The speed of the motor. That is our question, which is N2. Remember, this is the final one. When we had the original one, what is your N2? This is what you need to calculate. All right. Let's fill in our diagrams properly, the currents, this and that, what you're going to need. Remember, this is our generated EMF as you have to consider of the first, which is our original circuit. So we're going to call this E1. Then the armature current, that is part of the armature here. We're going to have armature current of the first circuit of the original. The field, I'm going to call this 1. All right, so this is it, what we need there. Considering the second one, the voltage at the terminals will just remain the same. So meaning to say you've got your voltage at the terminals, still your 200 volts, but definitely this will affect the load current. Remember your load current, this is 1 here. So you're going to consider this as the load current 2, a part of the field. Going to call this 2. If you check our diagram, in this case, your field does not change, still 100 ohms. If we check properly just because of our diagram, there is nothing that is connected to the field. The effect happened to the armature. So meaning to say, even on the calculation of the field current, according to this circuit, according to this, not to say always, but according to this, these two will remain the same. They will just remain the same because there's nothing that is affected there. Okay? Armature current is not going to change. As you had your armature current here, you're going to have your armature current 0.15 ohms. Then you have to consider calculating the generated EMF 2 in this case. All right. Here, you said we've got armature current 1. And this side, we are going to have what? Armature current 2. We do not know this. We do not know all this. Additional resistor we are given is 1 ohm. So this is it, guys. Remember your circuit, we're not gonna have much there on the circuit, guys. You know your circuit. Want to measure on the calculations there. So you want to calculate the speed at a final condition. This is your question. You want to calculate speed at a final condition. So I said back in our formulas, this is the first stage. The second stage is to write the equation for the speed control, which is your main speed control formula. So from our main, which is E1 over E2, considering what you're given, we remember there are 2 formulas there, but from what we have, we are not given anything that has to do with flux. Remember, flux is proportional to the field. So if you're not given flux, work with what? With the field. So you're going to use the formula with the field. Remember on those formulas that I listed before, like I said, as for me, I cannot able to show you because it has been removed, but you can just reverse your video for the sake of understanding. This is what we had. Remember, there were 2 formulas there. There was the one that had the flux also, here flux too. But we're not going to use that because we have nothing there. So this is it. You need to calculate this. This is what you're asked to be calculate. What are we given? The speed N1 is there. Are we having E1? We are not even having this. We are not having this. We are not having this. We are not having this. Check your diagram. You do not have this. So that is where we need to calculate these missing values. All right, so let's consider from the original condition. What can we obtain from the original condition? Right? From the original condition. I'm just going to write in short, guys. From the original condition, which means from 1. What is it that we can obtain from there? What can we calculate from there? Let's see. The armature current, we cannot because we do not have the field current. So let's think about the field current. Let's go back to our N4. Remember in N4, under a shunt, I said this is the same even if you check your electrotechnology. I talked about this. Okay, the voltage here is the same. The terminal voltage there. So meaning to say to calculate the field current was going to be easier because we simply use voltage over that resistance. So remember, you're using this as R shunt, but still it's the same, RF. This is what we're just using, guys. So you can have that because you have the voltage there back from our N4, N3. So we've got 200 over RF, which is 100. So you're going to divide, and that was going to give you the field current of 2 amps. So you're going to have 2 amps there. Okay, from your Kirchhoff's law, remember from your N4, if you're dealing with a shunt like this, you understand that the load current there is the sum of what? The field and the armature current. So you can make armature current by subtracting the field there. So it follows that the armature current is the difference between what? The load current and the field from your Kirchhoff's law. And that is your N4, like I was saying. In fact, N3, guys. This is your N3. So it's going to be load current minus what? The field current. So the load current is there, the field current is there. So let us just substitute and calculate our armature current from our diagram. The load current, remember, this is 45 amps. So we've got 45 that you're given there minus the final, the field, which is 2. Where am I getting this of the final, guys? All right, so this was going to give us what? 43 amps. With this is what we are having from the original condition. We calculated the field. It helped us to calculate armature current. Why are we calculating the armature current? It's not there. Because we know the armature current is needed on what? The generated EMF. Remember the generated EMF as I was illustrating on those formulas. I said for a motor, that's the back EMF V minus armature current and the resistance of the armature circuit. But this is from the original condition. So we're going to use 1 and 1 here to represent the original condition. So the armature current is there. This one is there. This one is there. The resistance, we just have to consider to say the resistance of the armature circuit. What is it that we have? This is a shunt where the armature current is flowing. There's only that resistance of the armature. So this is equal to the resistance of what? Armature circuit. We do not remember what I explained for a shunt. So unfortunately, guys, I can't show you immediately because it has been removed. So anyways, this is it. We have this. So this is simply the resistance of what? Of the armature that you're given. Everything is there. So we're just going to substitute. So E1, which is our generated EMF, was going to be calculated. Remember your voltage you were given from your diagram. This is 200. The resistance of the armature is what? 0.15. So just substitute your values there. 200 minus the armature current. We calculated this. It was 43. The resistance of the armature circuit from our diagram. We have it. So this was going to give us E1. If you calculate this properly, you are going to get 193.55 volts. All right. You have E1. Let's go back to our formula and see what is missing again. So this is now there. We calculated the field current is now there. This one is now there. So if you check, the one is, this one is not there. And this one is also not there. So let's think about this E, this field current, which is of the final condition. So from the final condition, let's talk about this. From the final condition, what is it that we are having? So from the final condition, all right, which is, can we calculate any of these two that are missing? Field current and the E2, the generated, which is our back EMF. All right, this is the final condition. Look at our diagram. Looking into our diagram, we can see that the field can be calculated. Guess what? Because it is the same, guys, we just have the voltage in, which is affecting in parallel. This is the same voltage. So we are going to have what? V over RF. Nothing has changed there. So that is, this one was going to be calculated according to this situation that we are having now. Because if there was something that was connected there, it was going to affect. But according to ours this time, guys, there's no effect. So there's no effect. So it's just simply a repetition of what we did here. 200 over what? 100, because it's the same. Nothing has changed there, which is 2 amps, according to this question. So if we consider F5, I think we had an example like this one, actually. So this is it. Then you have to consider that we now have this, which is needed on our formula. As of the armature current, as of E2, let's talk of E2, because we have now this. So we need to calculate E2. And we saw from these calculations that we had when we were calculating what? E1. You were going to be focusing on the generated EMF, but I want you to see what was going to happen using your generated EMF. It was going to be like this. E2 is equal to V minus what? Armature current times the resistance of what? Armature second. We are referring to 2. So as you have to calculate this, you were going to notice that you have V, the resistance of the armature. You just have to consider what is there. So this one can be calculated. But the armature current is not there. This one is not there. Original is not there. How were you calculating the armature current before? You had to consider the load current and the field because you were given the load current. This time, if you check, the load current is not there. You do not have that load current. It's not there. So what are you going to do? Because the load current is not there, but we need to calculate because the armature current is supposed to be taken from, it was supposed to be like this. Load current 2 minus the field current because of that Kirchhoff's condition. But this one is not there. And there is no formula. We do not have the power where we can use voltage times what? Current giving us. So that's where we think of what? That torque equation. From the torque, those formulas that I listed. Okay, it's unfortunate, guys. Like I said, I cannot show you back those formulas. But you have those formulas. If you have listed those formulas, that is where now you have to think of now from the torque. From the what? From the torque. What is it that we have? Remember there were formulas that there's so many formulas, T1 over T2. But which one is going to work? From that torque, we are going to consider where we've got the field current. There's nothing about the armature. I mean, there's nothing about the given armature current that we can calculate now. So that is the only thing that is left, the torque from this. And from that torque equation, this is what we had. Remember, T1 over T2. There are so many formulas that you can use there. But you have to consider where the field current is and where also the armature current is. So the formula is going to be what? Field current 1, armature current 1, field current 2, armature current 2. So I want you to take those formulas that I listed before. You'll see that we wrote this formula. So on this formula, remember what you need. You need to calculate what? From this one, you need to find what? Armature current 2. This which is missing on our EMF equation, on this EMF that we need to calculate. Okay, I have removed it. Okay, I removed it, no problem. But you need to calculate this as we saw that. So the relationship of T1 and T2 is that one that you are given. These ones, we calculated them. Remember, these ones, we have them, armature current. This one is taken from the relationship. The relationship is given that T2 is what? That's the given relationship, this one. T2 is equal to 0.8 of T1. So meaning to say we are going to remove T2 and write it in terms of T1. So there is no replacement of what? Of T1. There is no replacement of T1, but you have to remove T2. Write it as T1. In terms of T1, it was what? 0.8 T1, which is equal to all these guys we have. You calculated this. So just for the sake of time, but let's just substitute because we have it, guys. The field, remember this one? We calculated it was 2. Armature current 1, it was 43. Everything over the field 2, which is 2 amps, times the armature current 2, which is one that you need to calculate as you stated here that you need to calculate this armature current 2 here. Remember, this is the one that you need. So since we wrote T2 in terms of T1, it enables us, or it allows us to cancel T1 and T1 because they are the same. So you remain with 1 there. So you can even cross multiply to find this. You can even cross multiply. That's 1 times 2 times the armature current. Or you can even cancel because these two are the same, as we can see before you do the cross multiplication. Cancel this. You can see that they're the same. Then you can cross multiply. 1 times this is going to be armature current 2, 0.8 times what? 0.8 times 43. So that was going to give us the armature current 2 that we need, which was going to be 34.4 amps. So you're going to have 34.4 amps. With the 34 amps, which is our armature current, remember, we're supposed to just use this way. We're supposed to use this, but we're limited because we're not having the load current. And why are we calculating this as if it is needed here? It's not needed. It is E, which is needed here. It is that E2, this one, that is needed. So calculating this is so that we can calculate the E of the final condition, the generated EMF there. So E2 was going to be calculated. That is V. Remember, armature current 2, resistance of the armature circuit 2, as you are to consider that this is a motor. So all these are there. All these are there. So what is the resistance of the armature circuit considering the final condition? This is where those resistors now play a role. You have to check what is it that you had on our diagram. Remember, your final condition here. This is what is happening. Where the armature current is flowing, there's an additional resistor. There's the armature resistor. So the resistance of the armature circuit will be the sum of RA plus what? Additional resistor. I talked about this from the introduction of these circuits. So you have to add those two. So let's substitute, but not forgetting that you're supposed to add. So all these guys, you must put them in mind. All these is like you're getting back to your N3. Take everything that you had from your N3. So this is E2. V we're given, remember our V, it was 200 minus armature current 2. We calculated this was 34.4. As I said, the resistance of the armature circuit, we saw that was armature, and that of the additional resistor, and we are given this, the armature. Remember, it was 0.15, and that additional, it was 1. For the sake of us not having disturbances here, guys, let me just substitute direct. But you saw this from your diagram. So you can substitute after, then calculate. You're going to get 160.44 volts. This is your E2. So now we can say everything that was missing from our speed control formula. The main speed is there with everything that was missing. So we can calculate the speed, which is as we are given in our question, by substituting everything into our main speed formula. E1, as we calculated, we have to substitute everything. So E1, it was what? 193.55 over what? E2, the E2 that we just calculated now, it was 160.44, guys. For the sake of not having those disturbances, let me just substitute. Then N1, we have it. That was the speed originally given. I wrote it. You're supposed to write on the diagram there, 1,000. This is your N1 there, 1,000 times the field current 1. You calculated this. It was 2. Speed 2 is the one that you need to calculate times field current 2. Remember, you calculated this and it was just the same for this second. For this condition that you had, they were the same. Not to say always you're going to see that. No, just depend for this one. So this is 2 amps. So you are going to use this as 2. So remember, what is our question? Calculate the speed. So therefore, the speed can be calculated. So all these, guys, you will need this idea, the knowledge of each and every basic. So you're going to notice that it is just a different circuit that you're given. Otherwise, the calculation, they will remain the same. These ones. Like the stages, they will remain the same. The calculation, they will just differ according to what is the resistance of the armature circuit. But the stages are going to be a repetition. So you're going to see even other examples that you're going to see, but that is just a repetition that you are going to have. So at this stage where we are, we can now calculate the speed as we are being asked. And also seeing this, these two are the same, I can just cancel this. There's no effect. Cross multiply so that we can have our N2. So it's going to be 193.55 times N2 is equal to these two. They do multiply 100. It's 1,000 times 160.44. So we need this N2. So it's simply going to divide by 193.55. Divide also here by 193.55, so that these two can cancel and you obtain your N2, which is the speed there. So that is our N2. So dividing all this, simplifying all that, you're going to obtain the speed of 828.933 revs per minute, as we had everything before in revs per minute. So therefore, this speed also is going to be in what? Revs per minute. So like I said, let's go back to our N3 electrotechnology basics. N4, N5, all those, they are saying you know them. If not, we're not supposed to have taken all this time, but it's because you needed those basics. So because those videos are there, so you can just make yourself a favor, find time to go through those from electrotechnology, actually, the basics of your DC motors, because you'll be working with the DC motor as we are to consider what? As we are to consider this part of calculation of the speed control. It is the speed control of DC motors. So read about your speed, about your DC motors, the circuit diagram, possible circuit diagrams. If you know those possible circuit diagrams, then there is no effect. You see that it's just a repetition throughout. So let's meet in another class. Till we meet again.